So the next topic is basically to convert the oil equation into the Navier Stokes. But before starting, there's a concept that will come up. So this is a brief optional video that basically just covers vorticity real quick. So vorticity. Try to spell it. So vorticity. So the idea is there's like this blob of fluid. And basically what it could be doing is it could be rotating. So here's the center of the fluid. I got two lines coming out. And again, this is going to be the y and then the x-axis. I'm drawing that really well. See if I can get that way. Okay. X-axis. So I'm going to go through here. It's a little small. So these things basically would rotate. And each of these rotations is going to be spanned by an angle. This is going to be delta. I'm going to call it x. And this angle is going to be delta theta y. So then there's a few more things notationally that need to be down here. So this point is going to be x naught. This point is going to be x1. And then for the y side, that's going to be y naught. And then y1. That goes across over there. So that's just notation. And then I'm going to define this as delta x. I should erase this thing. Ooh. And define this across here as delta y. Okay, so it can be seen that delta x can basically be written as a function of velocities. So u again is going to be the velocity, and u is going to have two components. One is going to be in the x direction and another is going to be in the y direction. So u vector as usual is the velocity, and it's just going to be, u vector is going to equal ux and uy. And of course u depends on space and time, so u vector is actually u vector as a function of x, y, and t, and presumably this exists in all space. So the concept is to try to figure out how much did this rotate based on the velocity field. So the delta x is going to be basically equal to this. So there's this u vector, u at uy at x1 minus uy at x naught. So what this is saying is if this part is moving up and that part is also moving up, then of course there's not any rotation. So if they're both moving up at the same rate, for instance, it's not actually going to rotate. But if there's a difference in velocity, then there's going to be, like, this velocity at x1 is faster than this velocity at x0, then there's actually going to be a separation. So there's actually, this line here will actually rotate. And how much it separates, of course, depends on the difference between the velocities and then the delta t term. And then on the other side, using the small angle approximation, this would actually be delta x. So this is basically the radius times the delta angle is basically this distance going upwards. And in this case, the radius here is the delta x. So the delta x times the angle goes in and converts this to a distance, which is this distance. And the difference in velocity times the time is also the distance. And this, of course, also holds for the other side, which is the y term. So delta y, and it's going to be basically the same idea. Except that the signs are reversed. So this is negative y. Or ux, actually. y1. And this is at y0. That was kind of let me write that again. Okay, so rewriting this again, just going to take this over to the other side. So we have delta equals t, everything that's up there before. x0, and then divided by delta x. And the same thing for delta y. I'm going to have delta t again. And then everything that's here, negative. I think I'll actually put the negative out in front here and do the u. ux. One minus u x 0 and divided by y. Okay. So then you basically use an approximation to go ahead and rewrite this in terms of the partial derivatives. So the next thing to observe is that these things are basically partial derivatives. So, and I'm just going to do this for one side. So we have this uy x1 minus uy of x0 divided by the delta x, and that actually equals the uy of x naught plus the delta x minus the uy of x naught divided by the delta x. So that's just using the fact that by definition delta x is x1 is basically x naught plus delta x. That's just the definition. So this whole thing is basically going to approximate a partial derivative. So this basically goes like the derivative of uy with respect to dx. So the next thing to do is to look at this. So this term is what's right in there, basically. So this part right there is this guy. So I basically just showed that this part can be converted into this. That's basically where I'm going. So putting that all together is now a new equation for the delta x. So we start out with delta x, or delta, not delta x, but actually delta theta x is going to go like the derivative of t, which is on the outside, and then this thing just turns into that. So dy dx. And the same thing can be done over on this side for the theta y by taking into account that there's a negative sign in front of it. So now there's this theta, delta theta y, and this goes like negative delta t. And then this time it's du x dy. Because this is the transition, this is the ux, that is of course y naught plus delta y. So this is the derivative with respect to ux. What's the derivative of ux with respect to y is what this part actually is. So that's what it comes out as. Okay, and then the argument is for the complete rotation. So I'm going to draw this thing again because it's now off screen. So we have this thing, and this thing of course is rotating somehow. I don't like that. It's got some sort of rotation. But basically the idea is to take the average rotation and basically say, so we have this thing again, here, and then we have these angles, which are delta theta y and delta theta x. So the idea is, in order to calculate basically the rotation about this point, what's done is these two rotations are basically averaged. So what we're looking for is basically delta theta with respect to delta t. And the big argument is this basically goes like delta theta x with respect to delta t plus delta theta y with respect to delta t. And then to take an average, there has to be a 1/2 out in front of this. And so the next step is just use these equations that have been just derived up there. So that thing basically equals 1/2. And of course the delta t moves over to the other side. So I'll just write that out. Oh, no, actually, that this thing basically implies that delta theta x over delta t is going to basically go like dux, no, duy dx. Supposed to be y dx. And this thing, same basic idea. So delta theta y over delta t is basically going to go like uy dx. And so these equations can just be put into this, except there's one more thing I need to put in. That's a negative sign. So there was a negative sign out here. So this thing can basically go and then just substitute these things in to here. So this is 1/2, and then it's du y dx, and then minus dux dy. So basically, I'll write this one more time, so, and use one more notation thing, which basically says that delta theta over delta t, which is basically goes like d theta over dt. That should basically equal, symbol used for that most often is omega. That's just kind of by definition. That omega is the standard symbol for that. So basically omega, which is the rotational angular velocity, omega basically has been shown to equal 1/2 times these two derivatives, du over dx minus dux over dy. So what this turns out is, this basically gives a way of calculating how much the fluid is rotating around a given point. And so this is basically a measure of, this basically is a calculation for measuring vorticity. So vorticity, let me spell this right. Basically goes like the rotational angular velocity, which in turn goes like this combination of partial derivatives with respect to the velocity field. And that's going to be important later on in the actual derivation of the tensor for the viscosity. You can check this. Yep. So that is of that. So now I'm going to mess around with colors. Do that. Okay. There we go. Okay. So after that, the next videos will basically discuss the viscosity tensor and do a little bit of quasi-derivation. One more comment I should make is the source material for this. That is the source material for this. This is basically comes from the MIT course on the Navier Stokes equation for what looks like an 1801 course. And that's it for now.